So I'm going to be just talking a bit about innovation at the Council for Geoscience, or CGS for short. This is a disclaimer. It basically says that this is the work of the Council, and if I get anything wrong, please don't hold it against me. So just for those of you that are not familiar, the Council for Geoscience is basically the geological survey of the country. All countries have geological surveys, as many people are aware, and it was initially a completely sort of government controlled entity, and then it became a parastatal entity, which is still government controlled, but as was discussed earlier on, it has to get some of its own income. And this was done by the Geoscience Act number 100 of 1993, and it established the Council for Geoscience in its current form. So what do we do at the Council? Basically, we historically create maps of geology. So we promote the geology of the country for mining, and it can also be used for other projects like engineering and so forth. And we create maps across the entire country to do with the geology, which is a huge process and is also quite a time-consuming process. So the other thing that we do is we are a national advisory on geo-environmental pollution. So examples of this is mine-related pollution and so forth. And another thing that is probably known is that we manage the national seismic network. So anytime there's an earthquake and you hear somebody on the radio that's been phoned, chances are it's somebody from our organization who's discussing the actual earthquake. So what challenges do we have at the Council for Geoscience? Now, one of the reasons I wanted to discuss this up front is because this is kind of a practical talk. So in order to understand our approaches to innovation, you sort of need to understand our challenges that we have as an organization, which are unique to us. Well, partially unique to us. And it has to do with the fact that every organization has a different mandate or a different task, and therefore will have different needs that it has to fulfill. So geological mapping is the first challenge. It's very time consuming. Typically, historically, what would happen is a geologist would go into the field and he would wander all over the place. And every time he saw some bit of outcrop or rock or whatever, he'd make a mark on his map and say, this is what this is, and he would write it down. So you can see that it's extremely time consuming, extremely sort of labor intensive. And then the map would have to come back where it would be sort of collated and compared with other maps, and big mistakes would be fixed. So now, in a modern era, you don't really have time to do it like that anymore. Even if you had the manpower, it'd still be slow. So this needs to be accelerated, and it has been for many, many years, both by mining companies and geological surveys. And what it's accelerated through is the use of, say, techniques such as geophysics or remote sensing. But each type of data has its own limitations, which they need to overcome. Financial restrictions will always provide limitations. This is true of any organization. So this is a common challenge to everyone. Some specific challenges are things like remote sensing is very powerful for many organizations that map the land. But for geology, remote sensing has a little key problem, and that is that you have vegetation in the way. So if you want to look at a rock, there's no sort of magical way to get through the vegetation. The more vegetational farming that you have, the harder it is to actually work out what's under the ground because you don't have so much outcrop. Magnetic and gravity data is another technique that can be used. These look at the Earth's magnetic fields and gravity fields, and they measure things like magnetic minerals and dense minerals. They can look through the ground, but they can be a bit ambiguous, and only will look at those two things. Seismics is very popular globally. So seismics is used very heavily by the oil and gas industries, and gives you a good idea of the structure under the ground, but it's frighteningly expensive. It's not always something that can be intensely considered to be going across at the scale that we would like to go. And then the final technique, as an example, magnetotellurics is a technique that is used to look under the ground. It's actually far cheaper than seismics, but it's very sort of affected by things like railway lines and things like that in the neighborhood. So these are challenges that our organization faces, and this sort of sets the scene in terms of what we need to sort of improve on and develop. So I just wanted to mention again, just remind everybody about the definition of innovation, just to set the scene a little bit, also to show that innovation doesn't have to be some sort of scary, nebulous thing. So as has been mentioned before, basically innovation is the practical implementation of ideas or methods or products or services or solutions, and they result in a positive impact. what's interesting about the definition of any of the definitions of innovation that you find on the internet is that it's not the same thing as invention. And this is actually mentioned in multiple places. So invention is if you do something completely brand new. And I think a lot of the times when people think of innovation, they think of something that's just startlingly brand new, but it's not. It's actually just an improvement of a situation that has a positive impact. So not all innovations require a new invention, and not all innovations are an invention. It's not limited to technological advancements, and it can encompass novel approaches to problem-solving processes, organizational practices, or business model innovations. So I think that sort of basically points to you can have somebody that has an innovative approach to finances, in terms of a process, improving their processes and stuff like that. One of the nice examples I saw on the internet in terms of innovation, I think it might have been on the Merriam-Webster website, is that an example of innovation versus invention is that the telephone is an invention. It was a brand new thing. Nobody had ever seen it before. The cell phone could be regarded as an invention and an innovation because it improved on an existing technology, whereas the smartphone is an innovation. It hasn't done something dramatic enough. It's just an improvement. It's just basically somebody moving forward and working on something that exists. So bearing that in mind, what kinds of innovation opportunities do we have at the council? Well, we have a lot of data. And this consists of not only geological data, but geochemical data, which is databases of mineral elements, geophysical data, and so forth. And so one of the problems, or one of the challenges any organization that has lots of data has, is how well is the data being used. Sometimes data is acquired for a specific need, and it can be reused again for a different need, or sometimes the new opportunities arise. So improved data mining is definitely a place where we have tried to focus on in terms of innovation, bearing in mind that, for us as an organization, like any other organization, one of our constraints is the finances, and this is a reasonable constraint on any organization. If you have an infinite amount of funding, you probably would just get lazy. So being able to relook at old data and to try to make progress with it is very, very important. Software development as well is an opportunity. Many times, and that links up with postgraduate studies as well. So let me go with postgraduate studies first. Postgraduate studies is an obvious low-hanging fruit. The council is a research organization, and in the same way that, say, SANSA supports postgraduate studies and so forth, people at the council are encouraged to get PhDs and things like that. And any kind of PhD is, by very definition, has to do something new, which means it's got a high chance of linking up with something that's innovative. And a lot of the times when you're dealing with things like AI or machine learning, you're probably going to have to write up something in some sort of a language like Python, which actually links up to software development. So we're not talking about the software development of something that we've marketed and sold. We're more talking about the software development of something that can actually help in-house in an organization such as ourselves. And then two examples of technologies which synergize quite nicely with each other and that are something new that we're looking at are drone technologies and virtual reality. So some of the examples of the data that we have at the Council for Geoscience, which we would need to use to mine with, are geology maps, geochemical data, magnetic data, gravity data, seismic data, laboratory analysis of other forms. We have marine data, and we have access to a lot of remote sensing data, some of which would come through organizations such as SANSA, others of which we have had commercially flown and so forth. So this is all data that would need to be mined. And so the challenge over here for innovation is we have vast quantities of data and we need a way to speed up interpretation. Machine learning and AI present good opportunities to do this, but it's not without its problems. Done blindly, these techniques will produce bad results. So what I mean by this is that you have a lot of data, but you can't use things like machine learning as a blind way of actually approaching it. It's not a black box or a magic trick. If you can't see the manual way of finding your solution with that data, then the machine learning and the AI is probably not going to do the correct thing anyway. So you have to be able to understand exactly what the machine learning and the AI has done and verify it and check that it's actually done the right thing and it's done exactly what you wanted to do. In our case, a lot of the time when we talk about machine learning and AI, it is to accelerate a process because there's just so much data, it would take far too long to actually do it any other way. So in terms of data mining, one of the newer techniques, or one of the popular methods which has come about in recent years, is a thing called mineral systems. And the idea behind this is that you would take, you not only look at different data sets, but you also try to understand what mineral that you're actually looking at and how was it formed. And if you understand how it was formed, then you can maybe use that to narrow down which data sets and which aspects of data that you are interested. So for example's sake, you could have a type of data. You might know where a lot of, say, copper is through copper geochemical mapping, but then you need to maybe decide, does the copper deposit form close to a structure like a dike or a fault? And if so, you can narrow down your map until finally you have what you hope is a better deposit. And that's just through some form of machine learning, which would automate the process, as well as cleverly utilizing what data that you have. But techniques like this, which we find in the literature, often will need some sort of custom software, because you don't always have something off the shelf that you want to do, or you want to customize something to your own unique needs and so forth. So this led us to actually look into software development. Now, this is not an obvious thing that would come with the council, because we're largely a group of geologists and some geophysicists and so forth. So a lot of the staff members of the council wouldn't do software development, but it has actually found a place in it. You always find somebody crazy like myself that likes this sort of thing. So software development is very useful to explore new ideas and to check new possibilities. There's a lot of literature out there. It is surprising to see how much literature is actually not as recent as you might think. I mean, some of the things that are still being used today, that are commonly used in the cutting edge sciences, maybe decades and decades old. So Python is a popular language which has come about in the last couple of decades. It's a very powerful language. It allows easy implementation of machine learning and other concepts. And as you can see at the below, a list of libraries that we often use for our own development. And it's allowed us to actually innovate quite nicely with testing new concepts and so forth. So just as a reminder, this is a typical project process. You want to map an area, and in order to map that area, you need to accelerate the process for mapping the area. So you have some sort of airborne operation that collects data. In this case, the idea is that, say, the data sets would be magnetic and gravity data, and but now you want to be able to monitor, to interpret that data or accelerate the interpretation of that data. And so what we did is we developed some software to do this. So this is where the PGME project comes about. PGME stands for Python Geoscience Modeling and Interpretation. Often with Python projects, they'll have this pi in front of it. So it's not quite as original as it sounds. And it has started off being a 3D modeling and interpretation package, which we actually developed to be able to deal with geophysical data, such as what I just mentioned in the previous slide. And it has actually had quite a nice impact within the Council for Geoscience. We then expanded it to meet our needs. As we had a new software need that we would need, or a new need in terms of internally at the council, we would add functionality. And this functionality comes through these libraries I'm talking about. So you don't need to actually be an expert at everything. You just need to be able to know enough to be able to plug in the library that you want and take it from there. So cluster analysis, which is a form of machine learning. It uses a scikit-learn library, seismological functions for SciSan data. SciSan is a package which deals with earthquakes. Remote sensing ratios and improved imports. None of these two things are actually original. Lots of packages can do this, but we found that for our own needs, we needed something that would sort of batch and accelerate the process to allow us to get through data for our own personal needs quickly. And so we customized that. This project is actually released under the GNU General Public License. That means it's an open source project. Anybody can download it. Anybody can utilize it. So this is a way that the council can actually give back to anybody that is interested in this sort of thing. So this is one of the examples of something that we've done in innovation, trying to actually meet the needs that I've described before. And in terms of our mineral systems example that we said beforehand, We added the following functionality. We added structural complexity. Structural complexity is quite interesting. If you have a whole bunch of structures like faults or dikes or whatever, it not only would you see the faults and dikes, but it would basically see how many faults and dikes are clustered in an area, or what is the orientation of the faults and dikes in an area, and you can utilize that information to see whether or not there's some sort of pattern relating to whatever deposit you have. We added vector imports for geochemical data. We added vector graphing. We did machine learning. And then we put all of this together to be able to start approaching mineral systems. So this was something that we were able to do. We were able to test our own ideas through software. And all of this stuff was done basically, in front of a computer. It wasn't that expensive for us. I mean, mind you, this might be more unique to us. I know that many organizations have large expenses and they have no choices about it, but in our case, we were able to do this. So what challenges do you have with software development, as I've just mentioned? Well, you need specific skill sets. This is, I think, the biggest challenge. So you need people with an aptitude with programming. In our case, it would probably need applied mathematics of some sort, because if you're going to be dealing with machine learning or AI, that's going to be a skill that you need to link up with. And you'd need, for us, you need some sort of geology or geophysics background so that you can link that up with programming more naturally. You also need organizational support in terms of time. So the organization involved needs to know that that person can have the time to do the programming. It's not something that happens like in 10 minutes. You can't expect that. It is a job. So it's something that needs a bit of time. Virtual reality is another thing that we've looked at. So the idea, this is very new, and this is actually an ongoing project that we have. Now, virtual reality has been around for a while. It's also called, I forget what it's called, digital twinning. And the idea in our case that we want to look at is that when a person goes into the field, they look at a rock face or whatever, and they make notes and they take a photograph or two and they bring it back to the office. But in our case, it would be also useful to be able to actually have the field back in your office. So if you could actually construct a model of what you were doing in the field and then be able to look at that as if you were in the field back at the office. So it's potentially fulfills the need to bring the field to the office. And nowadays it's possible through a lot of off-the-shelf technology and software. I love games because games have, in the entertainment industry, has brought about a lot of technology that we can utilize in other industries. So in particular for 3D modeling, the gaming industry or the entertainment industry allowed for the development of modeling packages, which were more like CAD packages, but those principles then have extended to other areas, as well as things like now we see these VR goggles, which are pretty standard. Many years ago, you would have to have a whole virtual reality room that would be constructed. Nowadays, you just need a set of goggles and a web interface. So this has made it far more attainable to be able to look at virtual reality. And we can use both historical data at the CGS as well as data in the public domain. So what challenges does VR have? Well, in our case, it needs data because if you've just gone to the field last week, you obviously aren't going to have a historical data set that actually reflects what you were looking at. So you need to be able to have data collected in an appropriate resolution. You also need to process any old data since it's probably not in the format. So there are time constraints, but these are things that are achievable. You might be limited by the software because different packages and different VR things will be able to do different things, but that should actually improve with time. So that includes things like 3D format support and functionality in your packages. We basically use GIS package, which actually has a lot of support for this. So it looks like the industry is going in the right direction. But in terms of the data side of things, this is where I come to the final section of my talk, which is to do with drones. You can collect a lot of data with drones. So there are many commercial options available. And one of the great things about drones technologies is that you can actually have a lot of different sensors on these drones, but typically by default, they just have a camera on them. And just having a camera is enough to make a 3D model through photogrammetry, which is quite nice. It might not be the most accurate 3D model in the world, but it'll definitely be there and it'll definitely look like what you were looking at. But other sensors have become available that fit onto drones that are actually manufactured for drones, including hyperspectral, visible and near-infrared, thermal magnetometer, gamma ray spectrometers, and so forth. So these are things that we've been investing in at the council so that we can actually collect data via drones, and that will link up neatly with our VR technology. So applications of this include not only geological mapping, but also environmental projects where you need to actually get an immediate idea of what's going on to do some sort of environmental problem. So here is a data set that was collected to do with the drones. On the top right, you'll see the digital terrain model, which has been constructed through the drones. And in the bottom left, you'll see the area in terms of the photographs that it's collected. So it's actually quite nice. And here you could imagine using VR goggles, you can actually see the trench that was cut away, and you can with the VR goggles, you'd be able to go in closer and see exactly what the geologist was looking at in the field. And this can then be overlaid in GIS packages. So what are the challenges with drones? Well, they need to be in line of sight. This is a legal requirement. In order to be able to legally operate a drone, you must be able to actually see it the whole time, and that's quite a lot more difficult than one might imagine. Things disappear very fast. You need a CAA license if you're an organization. That can be time-consuming. It's necessary, but it is time-consuming. They're sometimes limited to a small area because of the battery limitation of the drone. And so if you want to actually carry equipment, you need to make sure you've got a big enough drone to carry it. And then, of course, equipment can be expensive. So in conclusion, for us, innovation is driven by the needs of the organization and the individual units in the organization. We found that it can make use of existing technologies and to improve functions within the organization. And for us, it is a driver of the CGS. It is something that we always are considering in terms of trying to achieve our mandate more efficiently. There are challenges, but we have found that they're not insurmountable. You just have to tackle them one at a time. And that's me. Thank you very much.